Hi class, welcome back to multivariable calculus. In today's lesson, we are going to practice evaluating triple integrals. So with single variable calculus, when we integrate, what we're doing is we are summing up the area underneath a curve, right? A curve in two space on the xy plane. So with double integrals, as we started using and practicing with last week, what we're doing is we are summing up the volume under a surface, okay, some surface with a given area. And so we're summing up the volume between the xy plane or whatever plane we're referencing and that surface. So now with triple integrals, what we're doing is we are going to be integrating in three, bounded by, with bounds set in three space, right? So we'll be integrating from some x lower limit to some upper x bound, same with y and same with z. And so we're still finding a volume, but now we're not limited to just the volume under a surface. So you could use, sometimes to calculate a certain volume, you could use double integrals or you could use triple integrals. So we're going to practice evaluating triple integrals today. And another thing you can use triple integration for is if you have a function for a density of some object, you can then calculate the mass of that object by integrating, using a triple integral and integrating density times dv. So let's begin with a warm-up. And what we're going to do is we are going to refresh our memories on double integration. So here's your warm-up. Looking at this double integral, you're going to go from 0 to pi over 2 and 0 to cosine theta of e to the sine theta for dr d theta. So try this out on your own. Pause the video and then resume when you'd like to see the solution. Okay, so looking at this now. So once again, we start on the inside. So it's going to be from 0 to cosine theta for e to the sine theta dr. Okay, so we're going to leave this integral alone on the outside, and we're going to leave this d theta alone on the outside. So then we're going to get, we still have the integral from 0 to pi over 2. And then what we're going to get is, well, there's no r in this exponential here, so it's just going to be r times e to the sine theta, so that part's not too bad. And we still have our d theta. And we're going to have to evaluate this from 0 to cosine theta. And so this is where it gets a little bit messy. So we still have our integral from 0 to pi over 2. And then we're going to have cosine theta times e to the sine theta minus 0 d theta. So I'm going to plug in my cosine theta for r. So we have cosine theta e to the sine theta d theta. All right, so this is a little bit messy looking. So what we're going to have to do is we are going to have to do a u substitution. So let's let u equal sine theta. That means that du is going to be cosine theta d theta. So solving for d theta, we get d theta is equal to du over cosine theta. So that means we have the integral of cosine theta e to the u du over cosine theta. So the cosines thetas will cancel out nicely, and we end up with the integral of e to the u du, which is much easier for us to evaluate. And so that is going to be, just plugging back in sine theta for u, we get e to the sine theta, and that's going to be from 0 to pi over 2. Okay, so sine of pi over 2 is going to give us, so let's see, let's write this out. We have e to the sine pi over 2 minus e to the sine 0. Okay, so sine of pi over 2 is 1, so that'll just give us e, and sine of 0 is 0, and so that would be e to the 0, which is 1. And so our answer is e minus 1. Okay, so now you're ready, hopefully, to move on to triple integrals. So let's start with an exercise. And what we're going to do is we're going to set up a triple integral that gives the volume of the solid region bounded by x is equal to 0, y is equal to 8 minus 2x, and z is equal to 8 minus x plus y, and z equals to 1. So let us start by considering the plane where z equals 1. So we're going to look at the plane where z equals 1. Okay, so when z is equal to 1, okay, so looking first at z is equal to 8 minus x plus y. So z equal to 1 gives us 1 is equal to 8 minus x plus y. And this is the, so let's see, let's subtract 8 from both sides. We get minus 7 is equal to minus x plus y, or y is equal to x minus 7. So let's try to tease out what we are looking at. So the plane of z equals 8 minus x plus y is going to be highest above the base, directly above the point 0, 8. Okay, so if we plug in 0, 8, right, we're going to get 8 minus 0 plus 8. Okay, so that's going to give us a high point there. And then letting x, so that would be if x equal to 0 and y were equal to 8, right? So let's think about the highest point. Okay, so we're going to have z is equal to 8 minus 0 plus 8 is equal to 16. So let's start to consider a cross-section first of our bounds, similar to what we were doing with double integration. So looking over here, we have y and we have x. So here's x and here's y. So what we're looking at here is we're trying to figure out what happens with these between these different bounds. All right, so what is really going on here and how are the variables related to each other? So looking at y versus x, let's start in the plane of z equals 1. Okay, so it's just like taking a sheet of paper and sticking it on the z-axis where z equals 1. Okay, so you can have any value for x and y there. Okay, so let's just look down at the xy plane. So when z is 1, we found out that x is related to y as follows. Y is equal to x minus 7. And so that's what this blue line is showing us here. This is y is equal to x minus 7. And we're also bounded by x is equal to 0. So we're bounded by x is equal to 0, so right here. So that's our left bound looking down. And so then we're also told that y is equal to 8 minus 2x is a bound. So that is where this orange line is. This is what the orange line is showing us, this y equals 8 minus 2x. So that's one of our given bounds. So this is just looking down at the xy plane. And so we're inside this region here. Inside here. Actually, let's do this with a highlighter. We can make this nicer. Erase, maybe. Okay, so I'm going to take a highlighter to it. So we're inside here. Okay. So then we can also try to figure out, all right, so what is going to be our max for z? All right, what's going to be our highest point for z? So we're already limited by our minimum for x because we're to the right here, going toward the positive x we're shading in. Our minimum bound for x is x equals 0. So we can't stick in a negative value for x here because we're limited by x equals 0. And so if we put in 0 for x, then we also need to think, okay, well, obeying these bounds, what's going to be our max value for y? Well, that's 8. So the 0.08 here is where we're going to get our maximum for z. Okay, so the point above 0.8 is where we get z is equal to 16. And so for z, we're going between 1 and 16, technically. So then this point right here is the point where y equals 8 minus 2x and y equals x minus 7 meet, right? So let's just put a little mark here. So at this point, we have 8 minus 2x is equal to x minus 7. So this is going to give us 3x is equal to 15, or x is equal to 5, for example. Okay. So let's set up an integral, and we're going to look at, so let's set this up. And so let's start by setting the x bounds. Okay, so let's start with x. And you remember, when you're setting up integrals, you can't have a bound that contains a variable on the outside. So let's start with our limits for x. So for x, we're limited by x equals 0 is our minimum. And so there, and then we found the point at which x is at a max. And that's going to be where we have y equals x minus 7 is equal to y is equal to x minus 2, 8 minus 2x, and that's when x is 5. So we're going from 0 to 5 for our x. So we're going from 0 to 5. So now let's set up our y bounds. And so now with triple integrals, your second integral in here can only have one variable for its bounds. It can't have more than one variable. So our minimum for our y bound can be defined by our x, since that's our outer integral. So let's define it by our x. And so our y bounds, the lower bound is going to be x minus 7. You see that, the blue, that's our lower bound for our y. So it's going to be x minus 7. And the upper bound for our y is going to be this y equals 8 minus 2x. So the upper bound is going to be 8 minus 2x. Okay, lastly, we're going to set our bounds for our z. And so the inner integral here can have up to 2 variables when we're dealing with triple integrals. And so for z, we're already told that one of the bounds is z equals 1. And we know that's our lower limit because we are able to come up with a high point staying within our constraints for x and y. So that is going to be 1, is going to be our minimum. And our maximum is going to vary depending on which x and y's we have. And so our maximum is going to be given by z is equal to 8 minus x plus y, which was given to us. So 8 minus x plus y. All right, and so then our inner integral is dz. Our middle one was dy. And our outer one is dx. Okay, so remember we set it up with bookends. So this outer integral is in terms of x, the middle one is in terms of y, and the inner one is in terms of z. And of course, looking at this, if we piece this together, dz, dy, dx, this is dv. Right, so we have a triple integral over some region dv. Okay, and so what we're looking at here in this inner integral, this 1 to 8 minus x plus y dz, it's a point that moves from z equals 1 to z equals 8 minus x plus y. And then moving outward, that's moving along the line segment that moves from y equals x minus 7 to y equals 8 minus 2x. And that's moving along the flat region that moves from x equals 0 to x equals 5. Okay, so now we have set up our triple integral. And we are ready to evaluate it. So I'm going to open up a new sheet for this. And this is our exercise 25.1. And I'm just going to write our integral up top so that we can refer back to it. So we were going from 0 to 5, x minus 7 to 8 minus 2x, 1 to 8 minus x plus y, and this was dz, dy, dx. Okay, so let's now evaluate this. Okay, so once again, we start with the innermost integral. So looking at dz, so we just keep the outer integrals exactly as they are. So from 0 to 5 in the x, and from x minus 7 to 8 minus 2x for y. And so if we integrate dz, that's just going to be z. And we're going to evaluate that from 1 to 8 minus x plus y. And we have our dy and our dx left over. And so this is going to become the integral from 0 to 5, and from x minus 7 to 8 minus 2x. Okay, so then we just need to plug in 8 minus x plus y for our z. And then we have to subtract off, plugging in 1 for our z. And we still have dy dx. And so this is going to become then the integral from 0 to 5, and from x minus 7 to 8 minus 2x. And then it's going to be 7 minus x plus y dy dx. So now we're just left with a double integral. So now let's just keep going. So this is going to be, so now looking at our next inner integral, we leave the 0 to 5 alone on the outside. And so now we have to integrate in terms of y. And so we're going to end up with 7y minus xy plus y squared over 2. And we have to evaluate from x minus 7 to 8 minus 2x, and we're left with our dx. Okay, so you can see this starts to get a little bit messy kind of quickly. And so now let's plug in. So we have from 0 to 5. And let's start then. We have our 7y, so it's going to be 7 times 8 minus 2x minus x times 8 minus 2x plus, now our y squared is going to be 8 minus 2x squared over 2. And then we're going to subtract off our lower limit, our x minus 7. So then we have 7 times x minus 7 minus x times x minus 7 minus, or plus, x minus 7 squared over 2. All right, and we still have a dx out here. So now we have to do some cleanup, and after a bit of cleaning this up, we're going to end up with the integral from 0 to 5, and we have 56 minus 14x minus 8x plus 2x squared plus 64 minus 32x plus 4x squared over 2. So that's just expanding out this first piece here. And so then we're going to have to subtract off 7x minus 49. And I'm going to continue down here. Minus x squared plus 7x plus x squared minus 14x plus 49 over 2. And then we still have our dx. Okay, so now canceling out, combining like terms, I'm going to add another sheet to continue on. So exercise 25.1. All right, so then we're going to end up with the integral from 0 to 5 of let's see, 56 minus 22x plus 2x squared plus 64 minus 32x plus 4x squared all over 2 oh, sorry, I was copying down the wrong line. Let me just erase that. Okay, 2x squared plus 32 minus 16x plus 2x squared plus 49 plus x squared minus x squared over 2 minus 7x minus 49 over 2 dx. All right, and so ultimately that simplifies down to the integral from 0 to 5 of 225 over 2 minus 45x plus 9x squared over 2 dx. Whew, almost there. So now we just need to integrate in terms of x. And so that is going to give us 225 x over 2 minus 45 x squared over 2 plus 9x cubed over 3 times 2, so 9x cubed over 6, which will be 3x cubed over 2. And that is going to be evaluated from 0 to 5. So we end up with 1/2 times 225 times 5 minus 45 times 25 plus 3 times 125, which is going to give us 375 over 2. All right, so just evaluated our first triple integral. And so let's try another one. So this time we're going to find an iterated integral that gives the volume for the region that I drew below. And so the unseen sides of the region are the coordinate planes. Okay, so this ZY coordinate plane makes up the back of this solid here. And the bottom is the XY plane. So let's start by looking at some cross sections. And so we're seeing that the bounds of the solid, right, one of the bounds is y equals 1 right here. And this face right here is y is equal to the square root of x. And then this upper piece is z is equal to 1 minus y. So let's start by looking at a yx cross section. Okay, so this will be 1. So this is looking down at the xy plane. And of course, this right here is 0. So we're bound first by y is equal to 1. Okay, so this is y is equal to 1. Okay, and so then our lower bound is going to be this y is equal to the square root of x. So this is going to be y is equal to the square root of x, right? Which is the same thing as x is equal to y squared. Okay. So this is just making it a little easier for us to visualize how to set our bounds. And now let's look at it again for z versus y, for example. Okay, so this back plane here. So this is z versus y. So for this, we have 1 and 1. And our bound here is going to be z is equal to 1 minus y, or equivalently, y is equal to 1 minus z. All right, so the thing is, there isn't just one way to set up an iterated integral. So we're going to try to set this up several different ways. So let's start with dz, dy, dx, that order that we did in our first exercise. So setting the bounds first for x. So based on x, our bounds are going from 0 to 1 for x, right? Because if we're limited by y equals 1, then x max here in this case is going to be 1. So we're going from 0 to 1. Now for our y, our max for our y is 1, clearly. But our lower bound for our y is limited by y equals the square root of x. So our lower limit for our y is going to be the square root of x. Okay, so this curve right here. And then for z, our lower bound for z is going to be 0. And our upper bound for z is going to be 1 minus y. So it's okay to have z just in terms of y and not x here, because our middle integral is in terms of y, which is defined by x, which will be okay once we get to our outermost integral finally in terms of dx. So this is going to be dz, dy, dx. So let's try to set this up in another order. So that's going to equal, let's put y on the outside. So y goes from 0 to 1. Okay, and so then let's do x next. So for x is going to go from 0 to all the way to the right here is going to be x equal to y squared. So it's going to go from 0 to y squared. And finally, z is still going to be from 0 to 1 minus y. And so this was dz, dx, dy. Let's try another order. let's do z on the outside. So once again, for z, we're going from 0 to 1. Let's do y next. So y in terms of z is going to go from 0 to 1 minus z. And then x is going to go from 0 to y squared. So this was dx, dy, dz. Okay, now we're going to do, there's 3 more combinations we can do, so let's set those up next. So exercise 25.2. Okay, so some other combinations. Let's put dy on the outside, so that's going to go from 0 to 1. And then let's do dz next. So it's going to be dz in terms of y, once again, which is going to be from 0 to 1 minus y. And then finally, let's do dx, which is going to be from 0 to y squared. And so that was dx, dz, dy. Okay, we have 2 more combinations we're going to try. So this is going to be equal to then, let's put x back on the outside again, and that'll go from 0 to 1. Let us do z next. So this z has to be in terms of x, okay? So this can get a little trickier. So what we have to do is, in order to figure out z in terms of x, we have to plug in, well, z is equal to 1 minus y, and y is equal to the square root of x. So in terms of x here, z is going to be equal to 1 minus the square root of x. We just plugged in. So we have 1 minus the square root of x. And then for our x, our y, x is on the outside. So we now need to define y in terms of x and z actually. So the lower limit for y is going to be dictated by y is equal to the square root of x. And the upper limit for y is going to be 1 minus z. And 1 minus z. Okay, so this was dy, dz, dx, and now we have 1 more to do, so let's put z on the outside, and that is going to be from 0 to 1. And now let's do x, and x has to be defined in terms of z. So for x, our lower limit is going to be 0, and our upper limit for x is going to be equal to y squared. And remember, y is equal to 1 minus z, so the upper limit for x is going to be 1 minus z squared. So this is going to go from 0 to 1 minus z squared. And then lastly, let's look at dy. And this is still going to be from the square root of x to 1 minus z. And this was dy, dx, dz. And so what I'd like you to do is I'd like you to select any two of these 6 to evaluate. So select 2 to evaluate. And you should get the same answer for both if you evaluated them properly. And I'm just going to go through one of them with you. So pause it, select two to evaluate, pause it, try it on your own, and I'm going to go through one of them with you. And so let us do the dz, dx, dy. So we're going to go from 0 to 1, from 0 to y squared, and from 0 to 1 minus y, and this was dz, dx, dy. So this is going to be the integral from 0 to 1, and from 0 to y squared. dz becomes z. We're going to evaluate that from 0 to 1 minus y. And this is dx dy is left over. And so that's going to be the outer integral still 0 to 1. And we have from 0 to y squared. And we need to plug in 1 minus y for z. And we have our dx dy. And so this is going to become, our y is still from 0 to 1, and integrate dx, you get x, so it's going to be x minus xy. And we're going to evaluate from 0 to y squared, and we still have our dy left over. And so if we plug that in, we end up with the integral from 0 to 1 of y squared minus y cubed dy, which is going to be y cubed over 3 minus y to the 4th over 4 from 0 to 1. And so we end up with 1/3 minus a 4th, which is 4 minus 3 over 12, or 1/12. So if you did them on your own, you should have come up with 1/12. And I'll just write it bigger over here. You should get 1/12. Okay, so let's move on and do another. So now with any of these, feel free to pause, try them out on your own first, and then come back to see the solution. So here we have describe or sketch the region of integration. And along the x, we're going from -1 to 1. For y, we're going from 0 to the square root of 1 minus x squared. And for z, we're going from 0 to the square root of 4 minus x squared minus y squared. Okay, so let's start by looking at y versus x. So we have y versus x. We have -1 and 1 for x. And so, actually, let me just draw this a little better. Okay. So now, along y, we're defined by, we're going from 0 for y, so that's y equals 0 down here, to y equals 1 minus x squared. Okay, so let's start writing down what we're doing. So for x, we're going from -1 is less than or equal to x is less than or equal to 1. We have drawn that out. 0 is going to be less than or equal to y. Is going to be less than or equal to the square root of 1 minus x squared. So the square root of y equals the square root of 1 minus x squared is going to give us a semicircle. This is going to be y equals 1. So it's going to be a semicircle with radius 1. And our lower bound here is going to be y equals 0. So we're in this region here. So that's just along the xy plane. And then if we think about z, like thinking about this now in 3 dimensions, we are going to be looking at our minimum is going to be 0 is less than or equal to z is less than or equal to the square root of 4 minus x squared minus y squared. So what we're looking at here is the plot of z equals the square root of 4 minus x squared minus y squared is going to be a hemisphere. So all we have to do is describe or sketch the region of integration. So we have a hemisphere above this semicircle here. So it'd be a region above the semicircle and below the hemisphere. So let's just write that out for our answer. So it's going to be the region under the surface z equals the square root of 4 minus x squared minus y squared, which is a hemisphere, and above the yx semicircle. Okay, right, where our x bounds are minus 1 and 1, and our y is bound between 0 and the square root of 1 minus x squared. So that's it for that. You just have to describe it in words. That's fine. And now we're going to do one more. And we're going to find the value of the following triple integral. And I'd like you to definitely try this one on your own. So pause it and then resume when you're ready to see the solution. So, of course, we start with the inner. So let's keep the outer integrals 0 to 3 and 0 to x plus 1. And integrate dz, and you get z from 2 to 4. We still have our dy dx. So this is going to be the integral from 0 to 3 and from 0 to x plus 1. And so we end up with 4 minus 2, which is just 2 dy dx. And so now we're going to get, we have to keep the outer integral 0 to 3 in terms of our bounds for x. And then we get 2y going from 0 to x plus 1 dx, which is going to be the integral from 0 to 3. And we have 2 times x plus 1 minus 0 dx. So this is just going to be equal to the integral from 0 to 3 of 2x plus 2 dx, which is going to be 2x squared over 2, which is just x squared, plus 2x. And we're going to evaluate it from 0 to 3. And so we're going to end up with 3 squared, which is 9, plus 2 times 3 is 6, minus 0. So that's going to be 15. All right, so go ahead, practice your homework problems on triple integrals, and I will see you next time. Take care.